Good evening. I'd like to say a few things about the second law of thermodynamics that your book did not take the time to discuss. And that's likely because your book tries to keep the scope limited. These chapters are long enough as they are. I mean, we're having enough trouble as it is just getting through the material that we were supposed to cover. But I think it's worth having this discussion because the second law of thermodynamics it's at the heart of everything chapter 21 is about. In order to understand the limitations on heat engines and refrigerators, you really need to have a gut sense about the second law. And one way of stating the second law, because if you've read the book or the chapter, you will have discovered that there's half dozen or more informal ways of stating the second law of thermodynamics. There's no one particular way of stating it. But the first way you should know of expressing it, is that if you bring a hot object in contact with a cold object, you can expect heat to flow from hot to cold, and never the other way around. I'm sure never in your life have you sat in front of a cup of hot coffee and watched the coffee get hotter and hotter as the rest of the room gets colder. That just doesn't happen. So consider two systems. It could be liquid water and a chunk of ice. It could be two different gases at different temperatures, or the same gas but separated into two volumes. It doesn't really matter. And I'm using these boxes here, these numbered boxes, to represent units of energy. And so the discussion I'm going to proceed with here is very similar to what you might find in a book on statistical physics. If any of you may major in physics in the future, you'll probably take that class. But the discussion that the line of thought that I'm pursuing here is really not 100% correct. It's not what you would find in those books, but that's to simplify it. The spirit is the same. So let's just run with this. It doesn't actually make sense to distinguish one unit of energy from another. I mean, a joule is a joule. You can't put a name tag on a joule of energy to distinguish it from another joule. So in that sense, this is misleading. But like I said, it's just a device that will help us simplify the discussion, and the conclusions are the same. So I've got 9 units of energy here, each of which is labeled by a particular number so that we can keep track of it. And over here in system 2, there are no units of energy. So this is a lot like having two gases next to one another, where this gas would be at a higher temperature. Because remember, temperature tells us about the average energy per degree of freedom in a thermodynamic system, which is just a fancy way of saying something that can contain thermal energy. And if I've got 0 units of energy here, that would indicate that this system is at an extremely low temperature. So high temperature, low temperature. What's going to happen when you bring these two into contact? So think of this red barrier as a partition that allows collisions to happen between the particles over here and the particles over here. And remember, these boxes here, these are not the particles. These are units of energy. You could still have a mole of particles over here, but if they're at absolute 0, they would have no units of energy. So make sure you understand that these boxes here represent units of energy, kind of like dollar bills. It's a currency. And this one's got all the money at the beginning, system 1. Okay, the arrows here indicate that heat can be transferred from one side to the other. There's a thermal exchange possible. So suppose that after such an exchange, we wind up with 3 units of energy, these particular 3, 2, 3, and 8, on one side, and then the other 6 are still in system 1. So that's a schematic way of saying that this is still at a higher temperature, or system 1 is still at a higher temperature than system 2, but the difference between the temperatures is not as severe as it was previously. And that would imply, if you think back to calorimetry, if the temperature of this one went down and the temperature of this one went up, that means that heat flowed from left to right. So again, heat flows from hot to cold. Okay, now suppose only 1 unit of energy, like if you went and measured the system at a particular time, if you had some means of determining the total energy in both of these systems at one instant of time, and when you do so, you find that there's a single unit of energy over here and 8 units over here. That's one way in which you could find that particular division. 1 unit in system 2 and 8 units in system 1. This is just one way of doing that. Another way of doing that would be this one. See that? Instead of the number 1 unit being over here, we could have the number 1 stay here and the number 2 unit be over here. So the energy apportionment is the same. We still have 1 unit in system 2 and 8 units in system 1, but the particular unit that's on the right side is different now. It's box number 2 instead of box number 1. Same thing here. You could have box number 3 on the other side. It's still the same apportionment of energy, 1 in system 2, 8 in system 1. It's just a different particular box that's been transferred to system 2. So all 3 of those possibilities that I just showed, this one, and this one, those are called 3 different microstates. The microstate is the exact configuration, which boxes are in which system. But because the apportionment of energy is the same, we would say that the macrostate is the same. Okay, so these are 2 different microstates. We can distinguish them because unit 1 is not the same as unit 3, but the energy apportionment is the same, and we would say that that means these correspond to the same macrostate. And what is that macrostate? Well, system 1 is still at a higher temperature than system 2, but the temperature difference is not quite as severe as it would be, in this configuration. Okay. I jumped past where we were. Okay. Instead of this particular macrostate, what about the macrostate for which there are 2 units of energy in system 2 and 7 units in system 1? How many ways could we do that? Well, let me back up. I think you can easily figure out how many ways there are to achieve this macrostate. If you've got 9 distinct units of energy, how many ways can you apportion the energy so that you've got 1 in system 2 and 8 in system 1? Well, you could have the number 1 unit over here, or you could have the number 3, or the number 2 unit, etc. So there's 9 possibilities. There are 9 microstates corresponding to this particular macrostate. Let's look now at this macrostate, the macrostate in which there are 2 units of energy in system 2 and 7 units in system 1. Now, if I gave you a quiz right now and said, hey, automatic A, if you can figure out in the next 20 seconds how many microstates correspond to this macrostate, you might get stuck, unless you had recently taken a math class where you covered this sort of thing, because we're really talking about combination. We're talking about the number of ways of choosing 2 objects from among 9 objects. So this is 1 microstate. You could take the number 2 and 8 units of energy, put them over here, or you could go with the 1 and 9, or the 3 and 5. You know, if you had all day, you could probably figure them all out, or maybe an hour would be enough. But there is a formula that allows you to calculate how many different microstates correspond to that macrostate. Here it is. It's 9 choose 2. That's how we read that, 9 choose 2. And you just take 9 factorial, you divide it by 2 factorial, and then you divide it by the factorial of the difference. And you could probably do this in your head because 9 minus 2 is 7. 7 factorial is 7 times 6 times 5, etc. And if you take 9 factorial and divide it by 7 factorial, everything from 7 down gets canceled when you're looking at the numerator. So all you're left with is 9 times 8 divided by 2. That's 72 divided by 2, so that would be 36. So if you had some time to think about it, you could come up with 36 different microstates corresponding to this macrostate. What is the macrostate? 2 units of energy on the right, 7 units of energy on the left. Okay, so again, for this macrostate, there were only 9 ways. For this macrostate, there were 36 ways. 36 compared to 9 is a factor of 4. So if we're just counting microstates, there are 4 times as many microstates corresponding to this outcome than there are microstates corresponding to this outcome. So if, when you go to measure the way the energy is apportioned, if each microstate is equally likely to happen, then this macrostate is 4 times as likely to be measured than this macrostate. Now, what does that have to do with what we've been talking about in this chapter? Well, again, there's a temperature difference between these two because there's more energy on the left, but this temperature difference is not as severe as this temperature difference. So by bringing these into contact and allowing them to exchange energy and by opening up these other possible microstates, in a sense, the temperature difference has been reduced, because when we go to measure the energy apportionment, we're more likely to find this macrostate than this macrostate. But even more likely than that would be this macrostate. Here we've got 5 on one side and 4 on the other. Now we can't divide them equally because there's only 9. We don't have, it's an odd number of energy units here. But now we can ask, okay, how many microstates correspond to this macrostate where there's 4 units of energy in system 2 and 5 in system 1? How many different ways can we choose 4 units of energy from among 9? Here's at least 2 different ways I'm showing you here. Same, again, these are the same macrostate, 2 different microstates. Here's another one, different microstate, same macrostate, where there's 4 units of energy on the right and 5 on the left. Use the combination formula once again. How many ways are there of choosing 4 units from among 9? 126. Well, that's significantly greater even than 36. So of all 3 macrostates that I just looked at, this is one of them where there's only 1 unit of energy on the right. Here's another one. There's 2 units of energy on the right. That was 36 microstates. Previously, it was 9. And then there's this one, which had 126 microstates. So by far, this macrostate would be the most likely to be measured because it has the greatest number of associated microstates. And what can we say about temperature here? Well, this is as close as we can get to an equal apportionment of energy. Now, if you're thinking, wait a minute, just because 2 systems are at the same temperature doesn't mean they have the same energy. You're right. Remember, temperature is the average energy per particle. If you had 2 quantities of gas and one of them had like 10 moles and the other one had 1 mole, then when you bring them into contact thermally, eventually they will end up at the same temperature, but the one with 10 moles will still have 10 times the energy. That's true. So like I said at the beginning of this video, this discussion is not as precise as it could be. It's not a perfect explanation for the concepts we're discussing. And that's because doing it this way is a lot simpler. Take my word for it. Or go pick up a book I can recommend to you, and then you'll see what I'm talking about. Okay, so I hinted at this a moment ago, but there's a postulate, I suppose you could say, from statistical mechanics. That's a very mathematical branch of physics. It says that when a system has reached thermal equilibrium, so you dropped some cold ice cubes into warm water, you wait a while for the 2 to reach equilibrium. At thermal equilibrium, all the microstates are equally likely. And that's kind of an abstract concept. It suggests that when you go to measure the way the energy is divided between the 2, you could find any particular outcome. Any outcome is equally possible. It just so happens that a whole bunch of those outcomes correspond to the same macrostate. The macrostate is what you would actually measure with a thermometer, a pressure gauge, etc. I mean, you can't actually know. You can't see how exactly, which energy cubes are in which box. Okay, so some macrostates are simply much more probable because they have more associated microstates. Now, in this example, the difference wasn't particularly stark because, and I'm probably giving you seizures here, but for this particular macrostate, we counted 9 different microstates. But how about the very first slide? How many microstates correspond to this macrostate? In other words, how many ways can you put 0 energy squares in system 2? There's only one way, and you're looking at it. This is the only possible microstate corresponding to that macrostate. So there's only one way. And here we had 9 ways, then it went up to 36 and then 126. So you can see that there's a stark difference, but it's not drastic. Now let's look at a system that's got way more energy available instead of just 9 units. And you may be thinking, is this even how it works in nature? Like, does energy come in little lumps that you can count? Strangely enough, it does. When you get down to the submicroscopic realm and you look at small quantum mechanical systems, energy actually is quantized. It comes in little lumps, and it can increase or decrease by 1 lump at a time, which is a totally foreign notion to our classical sensibilities here in physics. Well, post 3A. After all, this class is modern physics. You're supposed to be getting into all that stuff, but we kind of ran out of time here. Okay, so here are many more units of energy. I think it was 98 that I counted. And suppose they all start out in system one. So this would be like a gas at high temperature, low temperature. If you bring these into contact, do you really expect it to stay like that? Hot coffee, cold air in your kitchen room or your kitchen. Is the heat really going to stay separated like that? Or I should say the thermal energy. We know that some of this energy is going to make its way into the colder system. So again, this particular macro state where there's 98 units in one system and 0 in the other. How many microstates are there? Just one. You're looking at it. On the other hand, here's another macro state where we've got, I already forgot, 42. Yeah, 42 units of energy in system 2. And that would be 56. Yeah, 56 units over here. So that's a macro state, 42 on one side, 56 on the other. How many microstates correspond to this macro state? Well, obviously I wasn't going to take the time to number all these in PowerPoint, but if each of these boxes did have a distinct number, you can imagine there's a whole bunch of ways you could shift them around so that there's 42 here and 56 here. Let's not count them. Let's use the formula. I just typed this into Google. I said 98 choose 42, and it spat out this number. This is an insane number. You could never count this number. It's 10,000 trillion. That's greater than the mole. So the point is, as soon as you're talking about, and that's only 98 particles. How often do you encounter anything in the everyday world where you only have 98 atoms, for instance? Of course, I'm not talking about atoms. I'm talking about units of energy. But this is still a relatively small number, 98. And yet, the number of ways of dividing energy almost equally, this is not actually equal. I could have divided them up so that it was 49 and 49. Yeah, but I didn't do that. Despite the fact that it's not equally apportioned, we still have a crazy number of microstates. So this particular macro state would be way more likely than this one because there's only one microstate associated with this macro state. But this macro state has this many associated with it. So if all microstates are equally likely, you go to measure how the energy is divided between these two systems, you are way more likely to find this macro state. In fact, isn't it fair to say, let's say you made that measurement once a second. With this kind of ratio, I think you'd be waiting for the age of the universe and beyond before you ever discovered the system to be in this macro state. Okay. So this concept of entropy, your book touched on it in the previous chapter, and for whatever reason, your book chooses not to emphasize entropy in these chapters on thermodynamics. I think because it's a little more mathematical, and again, they're trying to keep the chapters limited in scope. But entropy has to do, one way of thinking about entropy is the number of microstates which are accessible to your total system. So if we go back here, before we put these two in thermal contact, see how there's no partition here? Or there's no thermally conducting partition. There's only one possible microstate available to this composite system because there's no way for this energy to get over here. So extremely low entropy because there's only one option available to the system, only one possible configuration. And that's akin to saying that you've got the maximum amount of information about the system. I mean, it's very organized, right? There's only one way to describe it. But as soon as we put them into contact and we allow energy to pass between them, now there's, astronomical is not even the right word. An uncountable number of microstates are now available because even for this particular macro state, where you've got 42 on one side and 56 on the other, there are this many microstates. Well, what about when you've got 43 on this side and 55 on the other? I think you would wind up with an even bigger number. What about when you've got 44 on one side and 54 on the other? You get the idea. There's just an incredible number of microstates available. So we say that the entropy of this system is now much greater than it was before. We know less about, like, what if you were just told
what the macrostate was. If you were just told that there's 42 on this side and 56 on the other, you actually still don't know that much about the system because you don't know which particular microstate it's in, because there are this many possible microstates corresponding to that macrostate. So high entropy, low information. Okay, back to the same example, just to contrast the numbers here. Again, there's only one way to get this macrostate. There's 10 to the 27th ways to get this macrostate. What about this macrostate, where you've got 3 units of energy on the right and 95 on the other? Here's a few, or here's just a couple different microstates. Well, 98 choose 3 gives us this number. That may sound like a high number. There's 152,000 ways to achieve that macrostate of 3 on the right, 95 on the left. But that's a piddly number compared to this number. So this macrostate of almost even apportionment of energy is still vastly more probable than this one. The difference is severe enough that you could really assert that you will never find the energy divided this way. Once you've brought these two systems into thermal equilibrium, and I know I didn't put the partition here, give them time to reach equilibrium, go to measure the energy apportionment. If you do that every second for the rest of your life, you'll never find it in this macrostate. Do it for the rest of the universe. I have no idea how long the universe is going to last. Whatever it is, you're still never going to find this macrostate because the numbers are so skewed. Okay, so I should emphasize that when you bring two things into thermal contact and allow them to reach equilibrium, you're imagining that they're evolving spontaneously. So there's no influence from outside. They're just two things. It's like the coffee and the air in your kitchen. Those are evolving spontaneously. Now you could rig up some sort of refrigerating device that actually does suck heat from the kitchen air and dump it into the hot coffee. That's possible, but then it wouldn't be a spontaneous process. We're imagining that we just let the system evolve on its own. So really the composite system, that's system 1 and system 2 in my graphic. So one way of phrasing the second law is that a system left to its own devices, so to speak, will always evolve towards a state of greater entropy, or at least stay the same. It will never decrease in entropy. So you would never, if you let the two systems reach equilibrium and you've got this possible way of sharing energy, they're never going to go back the other way. Like the energy is never going to make its way all the way over to system 1 and then have no hope of coming back. And I realize I'm being slightly imprecise in my description here, but that's kind of the price we pay for making this simple enough to discuss. Okay, so that's one way of putting it. You can phrase or couch the second law in the language of entropy, or you can simply say that heat flows from a warmer system to a cooler system. Because on average, if you look at all these possible microstates, on average, this system now has more energy than it had previously. Previously, it had none in my example. Now it's got quite a bit. And it's never going to go back the other direction. So hopefully this discussion gives you some better insight into the origins, I suppose you could say, of the second law of thermodynamics. It's really a statistical thing. Is it possible that your coffee would get hotter while sitting on the kitchen table on a cold winter morning? I suppose. But in the context of statistical mechanics, the likelihood of making a measurement and finding that were the case is astronomically low.